Hello, I am Pedro Rivera Cardona, and I will talk about my summer research project at MIT. With my advisors Jesse Taylor and Ricop Gambir, I worked on implementing periodicity into the energy float networks, which are machine learning models for analyzing collider events. I will give a background on the Large Hadron Collider and on my research project, as well as a problem statement and implementation of periodicity into the models. Then I will talk about the results gathered from a top core classification problem and the future extensions that are planned for the model. In particle physics, particle accelerators like the Large Hadron Collider are used to collide protons to study the nature of the fundamental particles of the universe. When colliding protons, the inner fundamental particles inside the protons, called quarks and gluons, collide to form other particles like heavier quarks like the top quark or bosons. Finally, these fundamental particles join to create hadrons like protons, neutrons, pions, or kaons that get detected by the Large Hadron Collider. This process is called jets, where by using algorithms, we can use the detected data to reconstruct these jets and identify them. Energy float networks are machine learning models used for learning from collider events that can be represented as sets of data points in space. Additionally, the energy float networks have infrared and collinear safety properties, which is a desired property for our purpose. EFN observables like the jet mass or the classification of the jet can be approximated arbitrarily well by this formula here, where by using the information of the particles inside of the jets, we can sum them up through the model to output the desired observable. Currently, EFNs can only do single jet analysis. Therefore, when confronted with an event that has more than one jet, the energy float networks cannot analyze both jets or more at the same time. This is because EFNs do not have periodicity. To assess this, we try to implement the U1 symmetry, which for our purposes is cylindrical symmetry. By extending the layers of our model, we can add an additional layer that will implement periodicity into the EFNs. This will be known as the U1 EFN. To compare the U1 EFN to the original EFN, we deploy both on a top core classification problem, where given information from an event, both models will predict the mass of the top quark that generated those jets, it being 150 GeV or 175 GeV. This is important because the top quark's mass is related to the Higgs mechanism, which is responsible for distributing mass to particles. We see that the U1 EFN can do full event analysis as intended, and it does obtain a higher score for jets that have a high transverse momentum, which means they move faster. As well, it performs similar to the original EFN for jets that have low transverse momentum. We also see a successful implementation of cylindrical symmetry, where in the left plot we see that there's continuity between the top and bottom parts of the representation of data. In conclusion, cylindrical symmetry was successfully implemented into the energy float networks, as well as full event analysis is possible with the periodicity implementation that we performed. Future directions include adding more representations of this U1 symmetry group, as well as doing Fourier decomposition of the observables into these representations for analysis. We also want to deploy this model into public data sets like the CMS Open Data, which is data from an experiment at the Large Hadron Collider, as well as add this model into the Energy Flow Python package for public use.